Alright, everybody. Welcome to my stream. My name is Alex, and I do programming problems on stream for all of you. Okay. Alright. So today we're going to continue with what we've been doing before, which is the problem set from LeetCode 75. And, you guys know how I work by now. I really like problems with funky names. I really hate problems that are very mathematical, because I believe that learning programming should not require you to learn advanced mathematics first. And I already see a problem with a funky name. It's an easy problem, which is perfect, because today I don't have a lot of time, so I might not be able to stream for all that long. Okay, cool. We're gonna switch to Python, as usual. I like Python more than Python 3 because I also use Python Tutor. I use that in my class actually, so I'm really just extending what I use. Okay, let's get on with it. You guys didn't come here to listen to me ramble on. Let me get my face out of the way. Oh, you know what? My face is safely tucked away here. One day I'm going to learn how to enable chat on stream. I think that day will come when I actually have viewers. Right now, my streaming schedule is too inconsistent to have any sort of viewership. People don't show up anyway. People don't even show up to my classes all that often, to be honest. That makes me very sad. If you're one of my students, this is to you. Show up to my class, please. Alright. Today's problem is named Kids with the Greatest Number of Candies. I like this name. Cool. Let's read the problem as usual. There are n kids with candies. You are given an integer array candies, where each candy I represent the number of candies the ith kid has, and an integer extra candies, denoting the number of extra candies you have. Okay, so you have an array of integers. The length of the integer is the number of array is the number of kids. So there are five elements in this list. So ergo there are 5 kids, and these kids have 2, 3, 5, 1, and 3 candies respectively. I have extra candies, in this case 3. Return a Boolean array results of length 3, where results I is true if giving after giving the ith kid all the extra candies, they will have the greatest number of candies among all the kids, or false otherwise. So return a Boolean array that says, if I had these extra candies, I would be king of the hill. Okay? So, for instance, the kid with the most candies right now is kid number 012, kid number 2. Remember, we always start counting from 0. So this guy, let's call him Alice, Bob, Charlie, Danny, and Elaine. So Charlie has 5 candies. If Alice gets 3 candies, if I give all my extra candies to Alice, then Alice would have 5 candies, just like Charlie. So Alice would then have the greatest number of candies. So let's think about a strategy for doing this. Well, the most obvious way to do it is first find the largest number of candies. Let's be very exact with our phrasings here. The number of candies held by the kid with the largest number, with the most candy. Okay, so it will be this guy here. In this example, we're looking for 5. Okay, so this is this is not an index, because an index tells us which kid it is. We don't care which kid it is. And we don't care about you, kiddo. Okay, this is the count, the value, because the value is the number of candies. Alright, to do this, we're going to be very Pythonic here. We're going to use a built-in Python function called max. Max returns the maximum number of candies. The maximum the biggest element in the list. Okay? And now we are going to go through all the candies in list and say if through all candies if larger or equal. Is it larger or equal? Well, in this example, we see that when 2 is given 3 candies, so if Alice is given 3 candies, Alice will have 5 candies, which ties Alice with Chuck, who is the kid with the most candies right now. According to the question, it says that this should return true. So we are looking for larger or equal rather than strictly larger. So for this, there are a few ways we can do this. One is we can use a for loop. We can do for candies if C is larger, C plus extra candies is larger or equal to most candies. Then do something. Or, since we are learning Python, let's do it the Pythonic way. Let me just write it out in the traditional way first. The traditional way will go like this. We need to return an array, right? We say result equals empty. And we say if result plus equals true, else result plus equals false. Alright? And then we return result. So what this piece of code is doing is that it starts with an empty array, and for each kid starting with Alice, we say if Alice gets extra candies, would that be larger or equals to most candies? Would that at least tie this kid for most number of candies held? If it is, we'll add true to the results. If not, it adds false. So this would be how you do it in a usual language like Java or C++. But since we're using Python, we want to use a Pythonic idiom. So first of all, before I even do that, let's simplify this a little bit. Well, instead of doing it this way, if this adds true, if something adds false, whenever you see a pattern like this, something true, something false, then you can very basically simplify it to this. Let me just run it to make sure I'm not inting. Yeah, make sure I'm not doing something weird. Okay, cool. So this is correct. Alright? So you can always simplify it to this. This expression over here, which you are using in the if, this expression they're using in the if statement, as a condition, it's going to give you true and false anyway. So instead of saying if this is true, then true. If this is false, then false. Let's just use the true and false result directly and do it like this. Okay? Now, we're going to further simplify this by saying results equals. We're going to do this thing called list comprehension. One of these days, I'm going to just do a usual lecture on how these things work in Python, but I'm not going to do it for today. So list comprehension works like this. For C in candies. So what this is doing is saying, create a list. And inside the list, I want to say this result. This is the thing I'm going to put in the list. For each element C in candies, I'm going to put this element into the list. So if candies has 5 things, it's going to run this 5 times. Each time it's going to substitute the element in candies for C. So, well, you can read the code, and this should work. Yep. And as a general rule, I like to simplify this even further. You don't even need an extra variable here. You can just say return. And I'm pretty sure this should work. Okay. So we're done. Cool. So I noticed that it says it beats 74%. I'm pretty sure the reason why we beat 74% is because we use these built-in Python functions. Okay, built-in Python functions are going to be faster than you writing it out yourself. They are more highly optimized. Alright, it seems like we have time for another one. So let's try another one. Okay, get that little check mark next to me. Oh, feels so good. Let's try another easy one. It says can place flowers. You know, I really have a soft spot for. I have a soft, as you guys know, I have a soft spot for questions with cool names. And generally cool questions, like the balloon one we did the last time. Okay, can place flowers, 605. We have a long flower bed in which some of the plots are planted and some are not. However, flowers cannot be planted in adjacent plots. Given an integer array flower bed containing 0 and 1 means 0 means empty and 1 means not empty. Return true if n new flowers can be planted in flower bed without violating the no adjacent flowers rule, and false otherwise. Okay, so this is basically the you don't know problem, huh? You don't want to sit next to anybody else. You know, you're an introvert like me. You don't want to sit next to anybody else at lunch. Well, here's the lunch table. Here are these 2 seats are occupied, and these 3 are empty seats. So if you want, you can take the seat in the middle, and that gives you a place to go. But if the seats are like this, 1, 0, 0, 1. So in this case, even though there are 2 spaces here, we will not be able to sit in between them. Okay, so let's see. Let's think about it a little bit. I'm starting to see a pattern here. Before we dive in, let's think about the pattern a little bit. And I'm not sure, as usual, I don't have the answers to these. I've not seen this before. So I don't know if this is the right pattern, but this is my line of reasoning that I'm going to pursue anyway. Okay, think about it this way. Okay, let's look at the array here. This flower bed with ones and zeros. This is let's say these are the input arrays. Okay, input lists. If the space, let's just look at the zeros because we are planting things in the zeros. We don't actually care about the ones. We don't. Let me explain what I mean. We don't care if it's 1 1 1 1 1 0 1 or 1 0 1. These two things are the same to us. We only care about spaces. Got that? We only care about spaces, and specifically, we only care about contiguous spaces, sort of spaces in a sequence. So let's look at the pattern here. If there is one space, one contiguous space, and this doesn't have to be 1 0 1, it can be 1 1 0 1, 1 1 0 1 1 1 1. It doesn't matter how many ones there are. I really don't care. I only care about the spaces, right? So if there's one space surrounded by flowers, then I can plant 0 flowers. If there are two spaces surrounded by flowers, I can still plant 0 flowers, right? Because if I plant one here, then it will violate this guy on the left. If I plant one here, it will violate the guy on the right. This can give me 1 flower, this guy right in the middle. This 4 spaces, interestingly, also gives me 1 flower. Because after I plant, I can either plant a flower here or here. I can't plant on this space or this space. So I can plant in one of these 2 spaces. And once I do that, the other space becomes a 1 space and a 2 space. And neither of these are able to support more than, support any flowers, in fact. So what about this one? It can plant 2 flowers. Here and here. Okay, 1 space, 2 space, 3 space, 4 space, 5 continuous spaces. What does that tell you? It tells you each contiguous sequence of empty flower plots, the number of length L, the number of flowers we can plant in it is what's the pattern here? So it's L minus 1 divided by 2. So L divided by 2. L divided by 2. It's not quite L divided by 2. So it's L minus 1 divided by 2. L minus 1 divided by 2. Let's just do capital L. Right? So you see the pattern here. L minus 1 divided by 2 is 0. L, let's say 2. Right? How do I know it's L minus 1 divided by 2? Well, that's a great question. My first hint was that I see that these number of flowers 0 0 1 1 2, and I'm pretty sure the next one is also 2. These number of flowers grow at half the rate of L. So L has to go up by 2 for the number of flowers to go up by 1. This makes sense, right? You want to plant a new flower, you want a new plot, then you gotta do something, okay? You gotta do something. Okay, before we proceed. Okay, so this gives us a strategy. So the -1 is sort of like, you fiddle around with it until it makes sense. It could be L plus 1, it could be L divide by 2 minus 1. You just fiddle around with it until it makes sense. And this division is actually integer division. So we're going to divide it and take the quotient. We're going to drop the remainder. Okay, so there is an exception. I can think of an exception already. So let's say something like 0, 0, 1. Okay? How many flowers can I 0, 0, 0, 1. How many flowers can I plant here? Oh wait, 0, 0, 1. Yeah. How many flowers can I plant here? How many flowers can I plant here? Well, it turns out I can plant 1 flower here, even though there are only 2 contiguous. Is a sequence, continuous sequence of length 2. I can plant 2 flowers here because the start of sequence, the thing on my right, even though it breaks my sequence, it does not prevent me from planting a flower here. This is different from a 2 sequence that has a flower on the left. If the left side is a wall, then you basically don't do the -1, you just do the sequence is a wall, then do L//2 instead. Okay. If one side, so this also applies to 1, 0, 0. What if both sides let me see. What if both sides what if both sides are walls? Let's play around with it a little bit. Okay, when L equals 3, this gives you 2. When L equals 2, this gives you 1. What's the pattern here? This gives you, this is also 2. Okay. So it looks like I don't think this is quite right. I don't think this statement is quite right. Let me check. Okay. So let's see how it is. So this is 2. You can plant 1 here and here. This 4 will only be 1. And this 3 will be 1. Oh no. This is 2. 1. I see. So So L divide by 2. If both sides of the sequence is wall, then do L plus 2 //2 instead. Ah, interesting. Okay, gotcha. So these are my edge cases. So basically the idea is as follows. We are going to go through the array and we're going to look for contiguous sequence of empty zeros. Okay? We're going to look for contiguous sequence of empty zeros. And then we're going to decide how many flowers we can plant in this sequence, each sequence. That's the plan. All right. So I'm going to do 4 for flower and flower bed. If flower equals 0, if flower equals 1. So if flower equals 1, then okay, left equals to, let's say left equals to 0. Oh, we're also gonna need the index. So IDX in enumerate flower bed. So IDX flower. So left is 0. Right equals whatever it is. So at the beginning left is 0. Okay. If flower equals 0. Let's see. We also need previous, right? We need a previous. What happens when flower is 0? What do you do? Let's say we're here. Flower is 0. What do we do? Well, we basically don't do anything. We only do something when we are either the first. Okay, so we do something where the previous switches. If previous, let's just do prev. Okay, so here's what I'm doing. Basically, I'm identifying, I'm detecting if I'm switching from a flower to an empty space. So if flower equals 0 and previous equals 0 and previous equals 1. Aha. So that means I'm switching from a non-flower to a flower. Is this situation here? Flower. So previous is flower. Previous from a flower to a non-flower. Okay. Okay. So this second case is basically we're switching from empty space to a flower. Okay. So in this case, length equals to IDX minus left. Let's do left IDX. So this way we know that all the indexes have the word IDX in them, and all the values don't have IDX. Remember? It's a very tricky thing. Sometimes you mix up the values and the indexes and indices. So IDX minus left IDX. So for instance, left IDX is here. And then let's say let's say this one, right? So it's 0, 1, 2, 3, 4, 5, 6, 7. So we're index number 7. Left IDX is 0, 1. Okay. So left IDX will be the first 0. The first 0 in a sequence. And then IDX would, in this case, be the first flower. So this gives us the length of the sequence. I'll actually have to make the left index -1 because there is an edge case when it's 0, 0, when the left is 0. Then this is 0, 1, 2. Oh, actually this works. One, two. 2 minus 0 is 1. Yeah, that's correct. Okay. And then, so actually this, we already know what to do here, which is we'll just say equals to idx. And what this does is that we want to set left index to the first 0 in the sequence. Okay, so length equals idx. So remember, the main case, in the main case, flowers I can plant equals, remember this, L minus 1 slash dash 2. Length minus 1 slash dash 2. Okay, this is the main case. But we also have to consider the subcases. So if how do I know what the subcase is? If left idx equals to 0, and so the left one is 0, okay. Oh, we don't have to care about the right hand side not being 0, right? We don't have to care about we don't have to care about this case for now, because this case would appear here rather than here. So we have to do something else here. So flowers equals 1. So flowers equals 1 looks something like this. Okay, let's take this. This is a great example. Okay, so flowers equals 1. Previous equals to nope. Previous equals to flowers equals 1. Previous equals 0. Flowers equals 1. Previous is still not 0, because previous start from 0. Okay, flowers equals 0, previous equals to 1. So it'll trigger this case. This will trigger this case. Okay? And this case will be triggered by this, when you transition from a 0 to a 1. So in this case, left indexes should be 3. 0, 1, 2 should be 2. 3, 4, 5. 5 minus 2, length should be 3. Okay? Left index equals to 0. That means flowers I can plant. If left index equals to 0, it means it's this case. In which case I can plant one extra, well, not exactly one extra flower, but it acts as if your length is 1 more. Now, this is the funky case. If flowers equals 0 and previous equals 1, most of the time we don't have to plant flowers, because we're not ending a sequence. Most of the time, if it's here, if it's wherever, if we're not ending a sequence. The only time we end a sequence is when if flower or rather if I dx, when we are at the end, equals to flower bed, length of flower bed minus 1. Okay? This tells us that we are at the end. This tests for whether we're at the end. If index equals to length of flower bed minus 1. So 1 less than length of flower bed. So what do we do when we're at the end? We are at the end. Well, we do the same thing. We do length. If there is a final flower bed ending with on the right edge flower plot of the bed, flower plot sequence. Let's be very, very careful about how we name things, okay? Flower plot is one plot. Flower bed is the whole list. Flower plot sequence is a sequence of flower plots on the right edge of the bed. Okay? So in this case, we know that we're talking about this guy here. So this guy, I can actually plant one more. It can act as if its length is one more than this guy, because the right hand side is free. So in this case, instead of length divided by 2, you have length plus 1, and this will be length divided by 2. Alright, let's run it and see what happens. This may work, this may not work. It doesn't even start. I forgot. Oh, I need to return. Okay, something is wrong here. Case 1 is correct. So case 2 is wrong here. Why is case 2 2? Shouldn't case 2 be the same? Oh, there's an integer n. I see. Okay. Can I plant at least n? Okay. So it's just larger or equals to n. Okay, let's submit this and see if it works. Wrong answer. Oh, 98 out of 128. Hey. Why is this the wrong answer? Why is this the wrong answer? This is kind of funny. N equals to 1. Output false. Expected true. Okay. So this is kind of weird because there are no special cases here. It's just a good old-fashioned flower pot. Okay. can I return flowers I can plant? See what my answer says. It might be the math here. That's my guess. Why is it saying true or false? Let's see if this works. It shouldn't say true or false. It should say 1 or 2. You should say the number. Oh, expected false is 1. Oh, I see. I should probably get a premium plan on this. I don't get it. Why is this? I think my code is correct. Am I reading the problem wrongly? If a new flower can be any new flowers without violating the known non-adjacent flower rules and false otherwise. Expected true? False. Why is this false? Okay, flower bed. I didn't move my left index. Is it because I didn't move my left index? Oh, I think there's some logic here. I think there's a logical error here. Okay? So, I'm only moving my previous. If the flower is 1 and the previous is 0. When the flower is 0 and the previous is 1. Flower is 0 and the previous is not 1. Okay, so my previous start as 1. Okay? So my previous starts as 1. So my end is 0. Okay, my previous starts as 1. And let's say on the first item, flower equals to 1 and previous starts 0. Nope. Flowers equals to 0 and previous 1. Yes. So it comes to here. It comes to here. If IDX equals length of flower minus 1, which is not the case, it goes to left IDX equals IDX, which means left IDX is 1, previous would be 0. And then it just skips these. Next time it comes in is here. Flower equals to 1, previous equals 0. 0, 1, 2, 3, 4. When IDX equals to 4. It's going to give you 3. Length is 3. If left IDX equals 0, which is not the case, so 3 minus 1 / 2. Interesting. Oh, plus minus. Oh, god damn it. Gosh, I'm sorry. I shouldn't say those words in a child-friendly forum. Gosh darn it. plus minus length, not equals length. I see. Okay, so I fail on another one. Great job. N equals to 2. So this should be 2. And because it's on the right, it says 2 slash 2, it gives you 1. This should give you 1. That's strange. I don't get it. I think my result should be mostly right. Because after all, I passed 102 tests out of 128. So I'm clearly doing something right. Oh. Oh, length? Okay, I see. This is the problem. So length equals IDX. It should be plus 1. This is an off by 1 error. So look at what's happening here. So IDX is 0, 1, 2, 3, 4, 5, 6. Is 6 is this guy here. So the reason why I do this is because IDX would be the first index of the first thing that is past the sequence. This one right here, normal case, you know, IDX minus left IDX. IDX is points to this 1 over here, it's the index of this 1. So it's the first element that's past the flower bed sequence. But in this case, this special edge case, IDX is pointing to the end of the flower sequence. It's not past it yet. I have to add 1 to past it. Zero, 1. This is very strange. IDX minus left IDX plus 1. Either way, this should not matter. So it's this 3 right here that's causing a problem. Plus minus length over 2. That's not good. Let's stick this into Python tutor and see where we get. Hopefully we finish up soon, because I gotta go. I gotta go. Alrighty. What's test case? N is 2. Flower bed is this thing here. N is 2. Okay, visualize execution. Hopefully this doesn't take too long. Syntax error. Okay, let's move everything up by 1. Okay, so I'm going to go to here and here and here, okay? we're gonna stop only in 3 places. So we're gonna next. Okay. So we're here. Flower equals to 0. Index equals to 1. Okay, IDX is 1. So we're here. 0. Next. So left IDX equals to 0. Yep, that's the right thing to do. We're here. Alright, IDX is 1. So left IDX is now 1. And then prev equals to 0. That's correct. Okay, the next time we stop, we are now at IDX is 4, 0, 1, 2, 3, 4. This is again correct. Let's see if we can correctly deduce that there is a flower that can be planted here. So length equals to IDX minus left IDX. That means length is 3. If left IDX is 0, and it's not, then we do it by this. Otherwise, wait a second. Oh. It should be a little bit. Wait a second. Okay. Something is not right here. Okay, let's remove all the breakpoints. Flowers I can plant. Okay, we're at IDX 4, so we're here. Length is 3, that's correct. Flowers I can plant should be equal to length minus 1, which is 2, / 2. And flowers I can plant, which should be 1. Flowers I can plant is 1. Okay, so next time we want to stop is at the end. So next time we want to stop is here. Can I place a stop there? Okay. Now IDX is 5. Ignore. Flowers I can plant is still 1. IDX is 6. Oh, I see. So this only checks if it only triggers if prev equals to 1. So that's my error. That's my error. Instead of putting this IDX equals to plant inside of here, I should put it outside. If flower equals to 0 and IDX, so flower equals 0, so have reached the end of the flower bed. Last sequence is still open. Okay, this should work, I think. Okay, let's submit it and see what happens. Oh, that's brilliant. Now everything works. Perfect. And that took a little bit longer than what I was hoping for. But, well, at least we got it done. Put it aside. There's probably a better way to do this. Check this out. It beats 46%. Oh, it's sort of flaky. But, you know, there's probably a better way. There is probably a better way of doing this. One day, I'll figure out what it is. I think there are too many ifs. Well, in the large, we're sort of okay because there is only one enumeration. So we count the number of for loops. There's only one for loop. So we're not iterating excessively, but within each iteration, we can be a little bit smarter about what we do. Yeah, for instance, we can enumerate up to flower bed -1, and then we don't have to do this check except at the end. That's one thing we could do. Well, anyway, I'm not going to waste time polishing it. I think even if we can get it to run a little bit faster, it will not be good code. It will not be good programming practice. This is the style that we want. We can probably optimize it a little bit more, but we'll have to sacrifice readability, which is what we don't want to do. All right, that's the end of my the stream for today. See you later, alligators.